Hi everyone, this is our video example related to our lecture 25 where we are talking about psychrometric charts. So this is an example where we'll be doing more practice on that and actually using the enthalpy values that we find from the psychrometric chart to our energy balance. This is question 8.86 from the textbook on page 483. Read that, open it, and follow along this video example. So in this example, we have wet solids that are passed through a continuous dryer. There's hot dry air that will dry these wet solids, and it enters the dryer at a rate of 400 kilograms per minute, mixes with the water that evaporates from the solid. So you have a dry air that picks up some of the moisture from the wet solids to form this humid air. And the humid air leaves the dryer at 50 degrees C. We are given the composition of this humid air. It has 2.44 weight% water vapor. And then it passes through a condenser where it's cooled to 20 degrees C, and as it passes through the condenser, you're going to condense some of the water vapor that's in there. The pressure is constant at 1 atm throughout the system, and we have 5 different parts to this question. The first part is asking for the rate of water evaporating in the dryer. Parts B and C uses the psychrometric charts, and parts D and E uses the values, the enthalpy values that we found from the psychrometric chart to apply to the energy balance, and then using the energy balance to solve for Q. So before that, like we always do in every single question, let's go ahead and transfer this information into a process flow diagram and label it the best we can. So let's go back to the question. We have wet solids that pass through a continuous dryer. So we have a dryer down here, and there'll be a wet solids coming in, and at the same time, at some point, there'll be humid air that comes out, and then we're going to have a condenser. Okay, we have a wet solids that's coming in down here, and I'm going to call it stream 1. And this wet solids is going to be mixed with some dry air in stream 2. And we know that from here, the dry air is going to pick up some of the moisture and form a stream of humid air that will go into the condenser. So this is stream 3. From here, some of the water vapor is going to get condensed. So we have a liquid stream down here. And we have our vapor stream down here. I'm going to switch the notation on you actually, because there's one other stream that we haven't drawn around the dryer. So it is not explicitly stated, but as we have dry air coming in and these wet solids coming in, the dry air is going to pick up some moisture to get this humid air. Let's not forget that there's actually solids down here, which means there's going to be some dry solids that's coming out. So presuming that it actually picks up all of the moisture and completely dries the solids, so we have a dry solid, that's the stream 3 down here. I'm going to relabel this as stream 4. And then I'm going to have, this is the vapor stream that comes out, and this is the condensed water stream in stream 6 down here. All right, so this is our skeleton of our flow diagram. Let's go back through the question and start labeling what we are given. We know that the humid air leaves the dryer at 50 degrees C, which means we are given the temperature of this stream. We also know the composition of this stream, so we know the mass fraction of water vapor is 0.0244, 2.44%, and we have dry air as the remaining, so 1 minus of that, 0.9756. All right. We know that when it passes through the condenser, it cools to 20 degrees C, so we know the temperature here. And that's 20 degrees C. We are also given actually the first line that I missed. The hot dry air enters the dryer at a rate of 400 kilograms per minute. So all right, so that's all we have given. Let's finish labeling this diagram. This stream, we have most of everything except the overall mass flow rate of humid air, so we need an M4 down here. We don't know the amount of water coming out down here, so we have M6 here. We don't know anything that's going on down here, but we know that it is still dry air and water vapor, so we have 2 components in here. And down here we have our dry solids. We are going to presume that this is completely dry, so we only have solids down here. And to make it clear, I'm just going to say this is solids free, so there's no water vapor. Down here, we know it is wet solids, which means there's solids and then there's water. So I'm going to write it as the actual amounts, the actual flow rates down here. All right, so that's everything that we know. Eventually, if you read through in parts D and E, we're actually required to do, in part D, to calculate the heat required for the condenser. So we actually have a Q down here that's also an unknown. With that, that is our fully labeled diagram. Let's go ahead and circle our unknowns. And with that, we can continue with the question, look over that, and let's continue to answer this question. So now that we have our process flow diagram drawn and all our unknowns labeled, let's start to answer the questions. And in part A is asking what rate is the water evaporating in the dryer. So what we are really looking for is we already know the mole fraction or the mass fraction of the water in that stream. What we need is M4. So let's look at the dryer DOF real quick. We have 4 unknowns. And we have 3 species. We have the solids, we have the water, and then we have dry air. And that's all we have. There's no other specifications or no other equations, which gives us a degree of freedom of 1, which seems like we can't solve the dryer to get our M4. You could do the same for the condenser, which we'll do eventually. But if you look at the condenser, we are also short of equations there. The DOF is not actually 0 either. So now looking at this question more closely, what you're going to notice is that the solids cannot be solved. In terms of the solids balance, what you have is the solids coming in stream 1 is equals to the solids coming out in stream 3. Without knowing either one of them, this balance is pretty much useless. You can't do anything with it. And for the purpose of this question, we actually don't need to know the mass of the solids anyway. So what we're going to do is we're going to take out these 2 unknowns, and you're going to see that by taking out these 2 unknowns, we have 2 unknowns, and now we are down to 2 species, because the solids is gone, and it will give us a degree of freedom of 0. So all we need to do is to solve 2 balances. We're going to start with the dry air balance, and the reason why I picked dry air in this case is because stream 2 is just dry air, and we already know everything in stream 2. With that, actually, we calculate M4 right away. So with the dry air balance, we get an M4 of 410 kilograms per minute. We could potentially solve for the mass of water in stream 1 if we wanted to, but this is not what the question is asking for, so we're going to leave that. What we're going to calculate is actually the rate of water evaporating. So that's our XH2O 4 times our M4, and so the rate of evaporation is 10 kilograms per minute. All right, so let's move on to part B. Part B and part C is where we are going to start to use the psychrometric charts, so giving ourselves more practice at reading the psychrometric charts. And eventually in part D and E, that's where we use the values that we have looked at or we have found in parts B and C into our energy balance. So in part B, it says to use the psychrometric chart to estimate the white bulb temperature, relative humidity, dew point, and specific enthalpy of the air leaving the dryer. That means that is stream 4. And in part C, it says to use the psychrometric chart to estimate the absolute humidity and specific enthalpy of the air leaving the condenser. So that would be stream 5. So we're looking at streams 4 and stream 5. To use a psychrometric chart, remember we need 2 intensive variables. So let's look at what 2 intensive variables we have for parts B and C. So for parts B, where we are looking at stream 4, we are given the temperature. So we know the dry bulb temperature is 50 degrees C. We need one more piece of information. And in this case, it turns out that it's not explicitly given, but what we do have is the mass of water vapor and mass of dry air in that stream, which means with those 2 pieces of information, we can calculate the absolute humidity. Remember, the absolute humidity is the mass of water vapor over mass of dry air, and we already have everything solved in stream 4. So we can put those numbers in, and you can see that with that, we have an absolute humidity of 0.025 kilograms per kilogram of dry air. Now with these 2 pieces of information, we know exactly where we are at on our psychrometric chart, and we can read off the other pieces of information that's required. All right, before we go there, let's go to part C first and to figure out what 2 pieces of information we have. We need 2 pieces of information. In stream 5, we know the temperature is 20 degrees C. So what's the other piece of information? We know that in this case, because some of the water is condensed out, that means the water is in vapor-liquid equilibrium, or in other words, stream 5 is actually saturated. So the air in stream 5 is saturated with water vapor. What does that mean? That means a relative humidity of 100%, or essentially we are on the left boundary curve of the psychrometric chart. So because we know it's saturated, we know the relative humidity of 100%, or just the fact that we are on the left boundary curve, we have the other piece of information that the temperature is 20 degrees C. So we're going to use these pieces of information. Now let's go on to our psychrometric chart. Let's go back to part B, where we have a temperature of 50 degrees C and an absolute humidity of 0.025 kilograms per kilogram of dry air. All right, so 50 degrees C is right here. 0.025 is right up here. And so if we come across here and bring it down, we are right here in terms of where we are at on the graph. So the wet bulb temperature, remember the wet bulb temperature will follow the diagonal lines up to the left boundary curve and read off the temperature scale. So we're going to go right up here, up across here, and then so we are at 30, 31, 32, so between 32 and 33, and so we're about 32.8 degrees C. In terms of the relative humidity, we can see that here's the 30% curve, here's the 40% curve. Remember the relative humidity curves are right here. So we're somewhere between 30 and 40%. You kind of eyeball it, that's about 32% relative humidity. In terms of the dew point temperature, we go to the same saturation curve and read off the same temperature scale, but now we go across horizontally. So we're going to go right across this way and get to here, and you'll see that we are at 25, 6, 7, 8, and so somewhere between 28 and 29, and so I eyeballed it as 28.6 degrees C. The last one we need is the enthalpy of that stream. So this is not a saturated stream, which means we need to read the enthalpy at saturation, and then we need to read the enthalpy deviation. The enthalpy at saturation, you follow the diagonal lines and keep going until you hit the scale, the enthalpy scale, and so from there it's about 116, so that's why I read the enthalpy. In terms of the deviation, you can see that we are between 1.0 and 1.2, minus 1.0, minus 1.2, and we are closer to the minus 1.0. So I took it as about a quarter of the way through, so it's minus 1.05. With that, you have an enthalpy of 114.95 kilojoules per kilogram of dry air. All right, so that's for part B, where we're looking at stream 4. Now let's look at part C, where we're looking at stream 5, which is a saturated stream, which means we are on the left boundary curve, 20 degrees C. So we're at 20 degrees C right here. This is where we are at. We are at the left boundary curve. So in terms of the absolute humidity, you just read across all the way right here. And it's just under 0.015. Again, I'm eyeballing it to be 0.0147. And then in terms of the enthalpy, all you have to do is read up to that scale, and it's about 57.5 kilojoules per kilogram. This is a saturated stream, so there's no deviation to talk about. All we have is the enthalpy at saturation. All right, with that, we can now put everything into our energy balance. So we're supposed to use the results that we just got from the psychrometric charts to calculate a couple of things. The rate of condensation of water, so that means we want M6, and the rate at which heat must be transferred from the condenser. So that's what we want Q. So the two things we want is Q and M6, which means we are actually solving the condenser system in this case. Let's quickly look at the degree of freedom to see what tools we have to solve. Remember that M4 has already been solved. We solved for that using the dryer. So in terms of the number of unknowns, we have 4 unknowns that's circled on the diagram. We have 2 species. We have dry air and water vapor. We have 1 energy balance, which is our to solve for our Q. And now the other piece of information that we have from the psychrometric chart in part C is that in stream 5, we know the absolute humidity. And the absolute humidity gives us the ratio of mass of water vapor to the mass of dry air, which means it gives us the ratio between these two unknowns. That gives us 1 additional specification. That will allow us to solve for all our 4 unknowns. Let's go ahead and do the material balance part first and then move on to the energy balance. So we're going to solve our material balances using 1 specification, the absolute humidity, as well as two balances that we have. So I'm going to start with the dry air balance. In terms of the dry air balance, I know everything that's coming in and know I can solve for what's coming out right away, and it's 400 kilograms per minute. This number might look familiar to you because that's really our basis right here. If you do an overall balance and you see that dry air only comes in there and it has to come out over here. So it's 400 kilograms per minute. From that, we know the mass of dry air. We can use a specification to find the mass of water vapor in that stream. So we have 5.88 kilograms per minute. With that, we just have one last balance to do. We can either do an overall balance or water balance, either one we find. I did an overall balance, and from there I found the rate of condensation, which is what we're trying to find, is 4.12 kilograms per minute. All right, so now let's go on to our energy balance. That's where we're going to find Q. Using the open system energy balance, making the same assumptions that we always have, we see that Q is equals to delta H. Expanding it out, it is the sum of all the output streams minus sum of all the input streams. So in this case, we have 5 and 6 as output streams, 4 as input streams. And typically what we say is every species has its own enthalpy. So every species you count as one term. So ordinarily before using a psychrometric chart, we would say that there will be 2 terms in 5, 1 term in 6, and 2 terms in 4, which will give us 5 terms in this entire energy balance. But now we are using the enthalpies from the psychrometric charts for both stream 4 and stream 5. The enthalpy values given on the psychrometric chart is an enthalpy of the entire stream, which is the mixture of both water vapor and dry air. And it is given per basis of dry air, which means that the enthalpy value is of the entire stream of 4 and the entire stream of 5. We do not have to split it up into 2 different species for those streams, which means we only have 1 term in 5, 1 term in 4 because it's only H2O, and 1 term in 5, 1 term in 6, and then 1 term in 4. That gives us 3 terms. So now we can write that out. Here is the stream 6, is the mass flow rate of 6, which we just found, multiplied by the enthalpy of water, which is liquid at 20 degrees C and 1 atmosphere. And then we have our H5 and our H4, which we got from the psychrometric chart. What mass do we multiply it by? Remember, these enthalpy values are per kilogram of dry air basis, which means we only multiply by the mass of dry air in those streams to get the actual energies in those streams, not the overall mass of the overall stream itself. So with that, again, this is just to say H4 and H5 are defined per kilogram of dry air, so you only multiply by the mass of dry air. So what about the enthalpy of water? We can use table B5. We already said that the psychrometric chart for water, the reference state for water is very similar to that used in the tables, so we can just assume that the reference states are the same. Just pick the values from the table itself. So using table B5, we see that we can get a value of 83.9 kilojoules per kilogram. Now we have all the values that we need. We can put in all the numbers that we have, and from there we can calculate the Q, which turns out to be minus 377 kilowatts. So that's the amount of heat that must be transferred to the condenser for this process to happen. We have one more part on this question to go. This is more a qualitative question. So it's asking if the dryer operates adiabatically, what can you conclude about the temperature of the entering air, and explain why you think so, and what other information you need to calculate this temperature. So what we are trying to do is this T2. We need to explain what can we say about this temperature, and what kind of information do we need to calculate this temperature. So let's look at the dryer and look at the energy balance for the dryer. So this is the open system energy balance for the dryer, the same assumptions that we are used to, but in this case, we are told that the dryer is adiabatic, which means Q is 0 as well. Our energy balance comes out to delta H equals to 0. What we are trying to do here is we have wet solids, and we're going to pass in dry air, and somehow this dry air is going to pick up some of this moisture from the wet solids into the humid air. So just by intuition, as you think about drying something, you need energy, you need heat. So if there's no external source of heat, the heat must come from the dry air itself. So to vaporize the moisture from the solids without an external source of heat, that energy has to come from the dry air stream, which means the temperature of the dry air stream must be higher than the temperature of the humid air, the air that's coming out, or higher than 50 degrees C. So that's what we can conclude about that temperature. It must be higher than the output temperature of 50 degrees C. What do we need to calculate this temperature? What we need to do first is to write out or expand out this entire energy balance, this It looks deceptively simple. It's just delta H equals to 0, but remember we have to look at every single stream and the species in those streams. So here's our delta H, expanding it out, and this is equals to 0. So what do we have? We have the mass of dry air in 4 multiplied by the enthalpy in 4. So this is pretty much similar to what we did for the condenser, because this stream is common for that. We already have that. We need the mass of the solids multiplied by the enthalpy of solids. So that is for stream 3. And for stream 2, we have the dry air. So we need one for the dry air. And in terms of the other input, which is the wet solids, we also have the solids at the temperature T1, which we don't know, and the enthalpy of the water at that temperature. So what do we have and what do we not know? The circled ones are what we do not know. Everything else we already have. So let's look at what we're trying to do is trying to find T2. What can we use to find T2? If we know H2 right here, we can find T2. Because we know that it's dry air, which means it has no water vapor. That means it has a relative humidity of 0 or absolute humidity of 0. With just one piece of information and the relative humidity of 0, with an enthalpy value and a relative humidity of 0, we can use a psychrometric chart to read off T2 at that point. So we need to estimate H2. Remember, in this equation, this is equals to 0, so we're trying to solve for this. If we can solve for H2, we can use the psychrometric chart and we can find T2, which means we need to find every other circled unknown that is in that equation right there. So what do we need? Number one, we need the mass of solids, ms3 and ms1. They're just going to be equal, so we need the mass of the solids that's coming in and out of the dryer. We need the temperature of the wet solids, so that's temperature T1. That will allow us to calculate the enthalpy of the solids and the enthalpy of water vapor in the wet solids. And we need to somehow be able to figure out the enthalpy of the solids by some thermodynamic correlation. So we need the heat capacity of the solids, and with that we can actually calculate the enthalpy of the solids itself. So those are the pieces of information that we need before we can solve this equation for H2, which will allow us to calculate T2 from there. So that's all we have for this example. There's one more example that will be very similar in terms of drying, but it'll give you some more practice in terms of psychrometric charts and using the enthalpy values in our material and energy balance. Work hard, be smart. I'll see you then.